Okay, so we've gotten a chance to see what projectile motion looks like, how we would handle projectile motion, one form of motion in 2 dimensions. Let's move on to another one. Another common form of two-dimensional motion is circular motion. Now, circular motion can be sort of drawn like this. Of course, you are moving in a circle, so there is a circle. And circles are characterized by their radius. So this little dotted line out here is the radius. It's given by lowercase r. Now, let's think about the actual motion itself. When you're traveling in a circle, and as I've drawn it, this object would be moving counterclockwise, your velocity is always tangent to the circle. That is, if you put a straight line right up to the edge, where it points is your velocity. But of course, at any point on this circle, that velocity points in a different direction, eventually pointing in all 360 degrees before coming back around. So circular motion has a velocity that's direction is always changing. Now, what do we call a velocity that is changing? We call that acceleration. So, this object is being accelerated this entire time. However, I'll point out that the speed is constant. That is the magnitude or amount of velocity. If you're going 30 miles per hour, you're always going 30 miles per hour. The only thing that changes is direction. But velocity is a vector. So changing direction is changing velocity. So this thing is accelerating even though its speed is constant. Speed is just the amount or length of that velocity vector, and that stays the same. What changes is the direction it points in. Now, how do you do that? Well, you take an acceleration, but remember, if your acceleration points in the direction of velocity, it increases your speed. If it's opposite velocity, it lowers your speed. So we need to find something right in between, and that is something that's at right angles to velocity. And so if I want to make this left turn, I need an acceleration to the left. It's sort of just pushing, nudging my velocity vector around and changing its direction as it goes around this circle. And so you can see on each of these three snapshots, these 3 moments in time that I've drawn, anywhere there is the velocity, the acceleration is always perpendicular to it, at right angles. And it's actually pointing directly towards the center of the circle. Now let's think of circular motion in terms of Newton's laws. So Newton's first law tells us that we must have a net force if we have a changing velocity. There must be a net force to change velocity. Remember, an object in motion remains in motion in a straight line unless acted upon by an outside force. So to change its direction, to not go in a straight line, we need an outside force. And Newton's second law tells us that if we have some net force, that's going to give us an acceleration. F equals ma. If you've got a net force, you have an acceleration. So really, I could have drawn a force in this direction either. We're giving a push to this object that's moving in a circle. And this gives rise to our 2 quantities we'll discuss, 2 new variables from circular motion, and those are centripetal force and centripetal acceleration. Centripetal means center seeking. So a centripetal force is really a center seeking force, or a centripetal acceleration is a center seeking acceleration. Remember, these accelerations, if velocity is tangent to the circle, acceleration, if it's at right angles, will be pointing directly towards the center of the circle. And the force vector needs to be pointing in the exact same direction as that acceleration. Both of them would point towards the center of the circle, which is why they are called centripetal force and centripetal acceleration. That is the force that makes you travel in a circle, and this is the acceleration that results from it. that causes your velocity to turn. Well, let's look a little more at these two quantities. Let's go ahead and jump right into equations for them. How would we compute the acceleration necessary to go in a circle? What amount of acceleration is the right amount to cause us to turn in a circle? Well, there's a lengthy derivation using some geometry that we're not going to get into, so I'll just hand you guys an equation here. And it looks like this. Centripetal acceleration, so I've used our traditional letter A, but here I've given it a subscript of C to represent centripetal acceleration, is given by your velocity squared over the radius of the circle that you're moving in. Well, what are the units of centripetal acceleration? You might have a guess based on its name, but let's take a look. Velocity, we know, has units of meters per second. If we square it, that becomes meters squared per second squared. We measure radii in some sort of length units. Our SI unit would be meters, so radius is going to have units of meters. If we put this together, the units of centripetal acceleration would be the units of v squared over the units of r, meters squared per second squared over meters. That is meters squared over second squared times 1 over meter. And we can see that meter cancels one of those two squared meters, and we're left with meters per second squared. Probably not a shock. We've already studied acceleration. We know the units for acceleration should be meters per second squared. You should have expected that result. Well, let's look at this equation again and think about it. Let's think about the relationship between each of these variables, the velocity and the radius, and how they might affect that acceleration. Remember, we talked about this in chapter 3. Directly proportional versus inversely proportional. Now, because the v squared is on top, it is directly proportional to the acceleration that is on top of the left side as well. That is, if the velocity increases, we need more acceleration to keep going in a circle. The radius is inversely proportional. It's on the bottom of the other side of the equation. So if our radius increases, our acceleration necessary to make a circle decreases. If r goes up, a goes down. That is why they are inversely proportional. And you guys can probably, picture this in your head. If you make a nice big circle, it doesn't take much acceleration. You don't feel much force, which is tied to acceleration. But if you try to tighten that circle, really crank your wheel in your cars or driving in a circle, whoa, all of a sudden you need a lot more acceleration and you feel a lot more force because of it to keep going in that circle. So big circles make for easy turns. Small circles make for tough turns. And similarly, the velocity, if it goes up, you're going to feel more force. If you try to take a turn too fast, you're going to need more and more force, more friction between your tires and the road to be able to make that turn. If you go nice and slow, low velocity, lower acceleration. You don't need as much friction between your tires and the road to make a turn when you're moving slowly. Furthermore, the v is squared while the r is not. That means that if we change the v, if we change our velocity, that has a stronger effect on the acceleration than changing the r. In fact, the effect is squared, just like the exponent would suggest. Well, lastly, now let's look at the equation for centripetal force. We've now already defined centripetal acceleration, and we're going to make use of that. Centripetal force, I've given an F, our typical letter for force, the subscript of C. And we know that F equals ma. So centripetal force should equal m times centripetal acceleration. It's just F equals ma, Newton's second law, but specifically for circular motion, specifically for relating centripetal force to centripetal acceleration. Well, we know what centripetal acceleration is, v squared over r. So if we just plug that in, we get mv squared over r. That is the amount of force necessary to make you travel in a circle. This is the amount of force to travel in a circle with this velocity and that radius if you are this massive. That is what that equation tells us. And of course, the units are the same as any force. We would expect units of newtons. We can take the meters per second squared that we had for acceleration. We multiply by kilograms. The kilogram meter per second squared is indeed a newton. So those are two new equations for motion in a circle. If you're going in a perfect circle, this is the amount of acceleration necessary. This is the amount of force necessary to cause that acceleration. All right, well, when we get back, we'll talk about two other topics before we close this chapter off. But next, we're going to talk about g-forces, which are kind of fun, something you've probably talked about, but you probably don't know exactly how to apply them in a physics sense. So we'll look at that next time.